Hello everybody. Today we're going to learn about DeMoivres theorem. Now, before we get into DeMoivres theorem, we're going to start with something that we already know how to do. So go ahead and try the equation that's on the screen and solve the equation x to the 6th minus 1 equals 0 for all solutions. Pause the video now, please, and solve this problem. Alright, so now that you've solved the equation, let's check your answer. So the most common answer that I see students give is this one right here. You add 1 on both sides, you get x to the 6th is equal to 1, and you take the 6th root and you get x is equal to plus or minus 1. Now this is two solutions. But if we remember back to our study of polynomial equations, we should remember and recall the fundamental theorem of algebra. If you don't remember the fundamental theorem of algebra, go ahead and pause the video and Google it. And what that fundamental theorem of algebra says is it says that we should not only have two solutions, but in fact we should have 6 solutions or 6 answers because we have a polynomial of degree 6. So that means that we have 6 solutions. Now, not all these solutions are real solutions. Some of them could be imaginary solutions. And in this case, we have 2 real solutions and we actually have 4 imaginary solutions. So if this is the answer that you got originally, please go ahead and pause the video and try and see if you can figure out another way to solve the problem so that you can get all 6 solutions, including the 4 imaginary solutions. All right, now that you've had a moment to rethink the problem, let's see how you did. Did you factor? We can factor this as a difference of squares. So it's really x to the 6th. And then we can think about 1 as 1 to any given power that we want. So we can think of x to the 6th as x cubed quantity squared. And then we can think of 1 as 1 quantity squared. So this is x cubed quantity squared minus 1 squared equals 0. So now with a difference of 2 squares, we can say that we have x cubed plus 1 times the quantity of x cubed minus 1 is equal to 0. And then with this, we can think about what we remember about the sum of 2 cubes and the difference of 2 cubes, and we can factor those accordingly using those two formulas for sum of 2 cubes and the difference of 2 cubes. Now when we do that, then we're going to end up with this. So we get x plus 1 times the quantity of x squared minus x plus 1, and so this x cubed plus 1 factors into those two factors. Similarly, we have x cubed minus 1 factors into those two factors. And with those then, we can solve each of the factors using the zero product property, forgot my equal sign there, and we can get the answers that are listed on the screen. Now, how did I get the answers from the x squared minus x minus 1 and the x squared plus x minus 1 because those do not factor? For these two, here and here, you are going to use the quadratic formula. So you can pause the video and just double check that you can get the same answers as me. And then of course, the very last thing we're going to do is we're going to write our final answers into set notation. So there are the 1, 2, 3, 4, 5, 6 solutions to the 6-degree polynomial equation. And now this verifies the fundamental theorem of algebra to show us that we do in fact have 6 solutions to this equation. All right, let's move into something that's new. Something that's new but similar. So we're going to find the 3 cube roots of negative 6 plus 6i. So we're going to relate what we're doing to complex numbers. And our complex numbers, this complex number is in standard form. Standard form, remember, is a plus bi. We also have trig form. Trig form is r cis theta. Or you can expand it and write it in the long form, r times the quantity cosine theta plus I sine of theta. All right, so we're going to actually use the trig form at some point in this problem. So if you don't remember trig form, please review that. So we want to find the 3 cube roots of negative 6 plus 6i. Let's think about what it means to find the 3 cube roots of negative 6 plus 6i. Another way that I could write this is I could say that this is the same thing as solving this equation. X cubed plus, or actually let me do this first. X cubed is equal to negative 6 plus 6i. If I asked you to solve that, you do the cube root on both sides. and you'd find the 3 cube roots of negative 6 plus 6i. I could move it over, so make it equal to 0, because we see a lot of times polynomial equations are equal to 0. So x cubed plus 6 minus 6i is equal to 0. So again, this is the same thing. These are all asking us to find the cube roots of negative 6 plus 6i. Okay, so all of these, actually let me include the beginning, all of these ask you to do the same thing. All right, so now understanding that, let's move into how do we solve it. So no matter how this problem is posed to you, you have 4 different ways that it can be posed to you, and you know that you're going to find all of these, okay? All right, so I mentioned that we're going to be using trig form in order to solve the 3 cube roots, in order to find the 3 cube roots of negative 6 plus 6i. So if we're going to be using trig form, the first thing that we want to do is we want to take this negative 6 plus 6i and convert it to trig form. So go ahead and convert negative 6 plus 6i to trig form. You can pause the video. All right, so what you can see is you should have found that negative 6 plus 6i is equal to 6 squared root of 2 cis 3 pi over 4. You can see in my diagram when I graph the coordinate of the representation of the complex number, I have an angle in quadrant 2, and therefore I end up with 3 pi over 4 as my angle. If you are doing the formulas and you are calculating the inverse tangent of b over a, you're going to get the inverse tangent of negative 1, and then remember to check the quadrant based on the location of the coordinates. Since this one is it has sides of 6 and 6 on the triangle, then you can use what you know about 45, 45, 90 triangles to get that the hypotenuse is 6 squared root of 2 without having to do the Pythagorean theorem. Otherwise, you do the Pythagorean theorem and that's perfectly fine. All right, so now what we want to do is we want to find the 3 cube roots of this trigonometric number. So the first one, so I'm going to call this the first root. Pardon my dogs. So the first root, we're just going to take this trig number, 6 squared root of 2, cis 3 pi over 4, and we're going to find the cube root of that. And to find the cube root of that, I know that a cube root can be written the same as a 1/3 power. So this is the same as saying that that's 6 squared root of 2 cis 3 pi over 4 to the 1/3 power. Now, you just learned something about the exponent rule with trigonometric numbers. So when we have trigonometric or complex numbers in trigonometric form, then we can apply this exponent rule. So let's apply the exponent rule. So what this is equal to then, we take the r value, which is 6 squared root of 2, and we take that to the 1/3 power. Then we take cis, and we take 1/3, and we multiply it by 3 pi over 4. So we can see here what's happening with the 1/3, it becomes the power there, and we're multiplying here. If you don't remember that formula, please review your previous notes. And so now I'm just going to simplify this. So then I can simplify the 6 square root of 2 to the 1/3 power. Well, now I have a square root and then I have a 1/3 power. So I want to remember my exponent and radical rules. So I know that square root of 2 is like 1/2 power, but I have the 6 outside as well. So I'm going to first put 6 square root of 2 into 1 square root. So put the 6 back inside, then that's going to be the square root of 72. Now the square root of 72 is to the 1/3 power. And then I have cis, and then this is simply pi over 4. And the square root of 72 to the 1/3 power, I want to see if I can simplify that more, which I can, because the square root of 72 is 72 to the 1/2. So this is going to be the 6th root of 72 cis pi over 4. And I can check the 6th root of 72 to see if that simplifies. If you're not sure, just make a little factor tree of 36, of 72, which is 36 times 2. Then it's 6 times 6. Then it's 2 times 3 and 2 times 3. And I see if I have any groups of 6 in there, and I don't. So that means the 6th root of 72 cannot simplify. And so this is our answer in trigonometric form for our first root. So this is one solution in trig form. Now, if you want to put it into standard form, you can. You can just expand out the cis pi over 4 and expand and do cosine of pi over 4 plus I sine of pi over 4. And we'll do that a little bit later. Okay, so that's just one solution, but we needed to find 3 roots. So to find the second root, scroll up a little bit, we are going to think about what this is on a graph. All right, so graphically, all of the roots can be represented on a graph, and they are represented and they have symmetry. So let's go ahead and graph this first angle or this first value and see where it's located, and then talk a little bit about that symmetry. So I have my R value is the 6th root of 72. So I'm not going to calculate exactly what that is, but I'm just going to make a mark here. This is going to represent the 6th root of 72. And then what I'm going to do is I'm going to draw a circle with a radius of 6th root of 72, because all of my answers are going to have that same R value. So this circle has the radius of the 6th root of 72. And then I know that all of my answers are going to fall on this circle somewhere. Now I look at my angle. So the angle that's given here that we found is pi over 4. So I think about where on the graph is this pi over 4. Well, I know exactly where pi over 4 is. So pi over 4 is going to be right here. So this point right there represents my first solution. This first solution is the 6th root of 72 cis pi over 4. Now, what's true graphically about all of the roots is that they are symmetric around a circle. So I have 3 roots in this case, and so I want to think about what angle would I need to have congruent angles to get from one solution to the next solution. And I think about what a whole circle is. So an entire circle is 2 pi, since we're working in radian here. And I want to have 3 solutions. And so I want to take that whole thing, 2 pi, and I'm going to divide it by the number of solutions that I have, which is 3. And so 2 pi over 3 is going to be the rotation from any one solution to another solution. So if I were to add 2 pi over 3 to pi over 4, and I were to rotate 2 pi over 3 more units from here, I'm going to rotate a distance of 2 pi over 3. So 2 pi over 3 plus pi over 4 gives me 11 pi over 12. So my next solution, my second solution, is going to be right here. I already know that that angle is going to be 11 pi over 12. Now, that's a rotation here of 2 pi over 3 from the first solution. And I'm actually going to change that one color to blue, so that the entire angle, this whole blue angle then, is 11 pi over 12. Okay, so that second solution is going to be right there. It's going to have the same R value, 6th root of 72, and now it's cis 11 pi over 12. And then my third solution. Well, my third solution is going to have the same relationship. So the same relationship is going to be that we are 2 pi over 3 from the last solution. So if I start with my 11 pi over 12 and I add 2 pi over 3, add 2 pi over 3 to that, then that's going to give me 11 pi over 12 plus 2 pi over 3, then that's going to give me my third angle, which is right here. And that angle from beginning to end then would be 19 pi over 12. So we have the 6th root of 72, cis 19 pi over 12. All right, so we actually have our 3 answers right there on the screen. They're shown on the graph, and we found them using the symmetry. Now, how do we find those algebraically? We do exactly what we did for the graph, but we just do it with the algebraic expression here. So our second root, what we did is we took the first root and we added 2 pi over 3 to the angle. So we're going to go ahead and we're going to do exactly that. So I take my first root. My first root is 6 square root of 72 cis pi over 4, and to the angle I'm going to add 2 pi over 3. And that's going to give me my algebraic representation. 6th root of 72 cis 11 pi over 12. And there we have our second answer. And then, third answer, same way. So we took our second answer, third root is just the second root plus 2 pi over 3 to the angle. So my second root was the sixth root of 72 cis 11 pi over 12, and then we're adding 2 pi over 3 to the angle, and that gives us our third root. So our third root then is the sixth root of 72 cis 19 pi over 12. And those are our three solutions in trig form. Okay, so when you write out your final answer, we're going to write out all the three of those into our list. And so we have the sixth root of 72 cis pi over 4, comma, sixth root of 72 cis 11 pi over 12, comma, whoops, the sixth root of 72 cis 19 pi over 12. We don't need set notation because it didn't ask us to solve anything. Remember, if we go back to the beginning, very beginning, it said find the 3 cube roots of -6 plus 6i. And those are our 3 cube roots then of -6 plus 6i. Now, if you wanted to put these into standard form, you would just expand out the cis and what that means. Because they're not all unit circle values, you would have to use your calculator. So you can go ahead and do that if you'd like, and I'll put the answers up so that you can check to see that you know how to convert this trig form into its appropriate standard form. All right, so you can see on the screen how you expand the cosine plus I sine, and you just use your calculator to calculate, and then you get your answers in standard form. So these ones are in standard form. And that's it for this lesson. So these are trig form. Thank you for listening.